Hi, welcome back to another 4AC work example. Today we are looking at example 4.3c, which is actually in your lecture notes. Now the question goes this way: a small industrial plant has a 10 kilowatt heating load, right? So 10 kilowatt heating load means I'll just sketch out something first. It's a resistive load because heating is resistive, so it's 10 kilowatt. So this is the one to use the word real power, and a 20 kVA inductive load, right? Inductive load, so I call it QL. Heating element considered to be purely resistive, right? And the AC motor have a lagging power factor. So if this one have a lagging power factor of 0.7, it means that it has both resistive and inductive element, and is connected to a AC supply. Right? AC supply at 600 watt, 50 hertz. So what we want to do is to determine the capacitive element required to raise the power factor to 0.95. Now, before we can do that, we need to determine what is the, the current situation. Excuse me. So the first thing we want to determine is the apparent power, the current apparent power, right? So I can just write it as 10 kilowatt. Now remember, we're dealing with very big quantity, so we just leave it as that. Now this is inductive, so I can write J. J 20 kVA. Okay. Now, I'm sorry. This one S1, it should be just purely the resistive. So here should be 0. Whereas S2, if you want to be consistent, S2 should be no resistive load, but there is a inductive load, right? Inductive load of it's not that there is none, 20 kVA, but okay, maybe I just write properly. 20 kVA with a power factor of 0.7. Now this means that it has two components in there. One is P2. P2 means okay, now it has this power factor is 0.7. So from here I can find what's the angle. Angle is equals to cos inverse 0.7. That's equals to 45.57. 45.57 degrees. Right. Phase angle between the factors. So here, if I want to calculate this, that should be the apparent power cosine 45.57. That gives me 14 kilowatt. That means 20 times 0.7, which is 14 kilowatt. And the reactive power is sine of 57 degrees. That's 20 times sine 45.57. Sine 45.57 is 0.714. 714, which gives me about 14.28 kVARs. Okay. Now that means if I write in rectangular form, it should be 14 plus J 14.28. Okay. All kVA. So now I can sum the two up to get the total apparent power. Now the total apparent power is S1. This S1 is just 10 kilowatt plus 14 kilowatt plus J 14.28. That gives me 24 kilowatt plus J 14.28 kVAR. Convert this back to polar form. That's about 27.927 at the angle of 30.75 degree kVA. Okay, so that is the total apparent power or complex power of the present system. All right. Based on this, now I want to do a correction. So therefore, the existing power factor is just this one, right? 30 degrees. Okay, maybe I'll just move it on to something else first. I still need this. So to make it easier, now I can just draw a power diagram. Okay, so currently the existing power diagram is something like that. This is the power as total. The resistive power or the real power is 24 kilowatt, and the reactive power Q is 14.28 kVAR. Now this one gives me an angle of 30 degrees 30.75 degrees, right? Now this is corresponding to one power factor, but I want to improve the power factor to 0.95, which means cosine of the new angle, correct, NEW, new angle must be 0.95, which means the new angle must be cosine inverse of 0.95, which is equals to 18.19 degree. In other words, now I want to reduce this angle to something like this. So this new, so this one is 18.19, which means I must introduce capacitive reactance Q C such that whatever's left here will give me this new thing, right? So working backward, the new so-called reactive power QT must be equals to the real power tangent of the new angle, right? Since the real power remains the same, so the real power from the original is still the same. Real power never changed, so that is equals to 24 tangent of 18.19 degrees. So that will give me a new reactive power of so much only, right? That means I only want something so short. That means I need to add in the reactive power so that I can get this. So minus the final one. So that's 14.28 kVAR minus 7.888 kVAR. So this is the reactive power that is needed to be provided by the new capacitor. But we also know that the relationship between QC can be calculated from this formula. Alright. In other words, XC is equals to the voltage applied 600 square divided by this value kVAR. So XC will be equals to 56.32 ohm. Now we also know that XC is equals to 1 upon 2 pi F plus plus the capacitance, right? So rearrange this formula. My capacitance required must be equals to 2 pi times 50 times 56.32 ohms. That gives me a capacitance value of 52 microfarad. Okay, so this is the capacitor I need to add on to the circuit, right, so that I can reduce the total power factor. Remember, we had a resistor like this and the inductor. So I need to connect. The power factor 0.7, and this is 4, this is 10k, right? Then I need to add a capacitor across here of XC equals to 56.32 ohm in order to improve the power factor. Okay, so I hope you have some idea about how to improve power factor in a circuit. Thanks for watching.